we will start with the Nucleon scattering. We have already mentioned that the nature of nuclear force can be studied by the interaction between the simplest system, that is deuteron, which contains only two nucleons, that means one proton and one neutron. And we have already mentioned that if you have an excited state for deuteron, and if there is a transfer from an excited state to the ground state or to any other state, you can have some more ideas regarding the nature of that deuteron you can study, or it will give you more insight into the nature of nuclear force. But unfortunately, we have no excited states for deuteron. And actually you can calculate for excited state of deuteron, you can calculate its binding energy or potential, etc. And this will show that theoretically also it is not possible. But for another way of calculating or another way of studying the nuclear force is if there is an interaction between two nucleons, and when they are coming close to each other, you can have a nuclear force. And that nuclear force, and the example is your scattering experiment. So when one nucleon is approaching another nucleon in a scattering experiment, and when they are within the nuclear range, there will be interaction between these two, and it will modify the nature of the path. So this technique is used to study the characteristics of our nuclear force. So here, the total amount of information about nucleon-nucleon interaction that we acquire from the study of deuteron is very limited. As far as we know, there is only one weakly bound state of the neutron and proton. And we have the configuration of deuteron is with L is equal to 0 and also parallel spins. That means I is equal to 1 and nearly 2 femtometer separation. We have considered as 2.15 is the nuclear range. And to study the nucleon-nucleon interaction in different configurations, we need to perform nucleon-nucleon scattering experiments. And there are two ways to perform nucleon-nucleon experiments. The first one is here, an incident beam of nucleons is scattered from a target of nucleons. Here you have a number of nucleons is there and it is scattered. The observed scattering of a single nucleon will include the complicated effects of the multiple encounters and is very difficult to extract the properties of interaction between individual nucleons. Because, for example, if you consider a single nucleon here, it can interact with all these nucleons. So, the result will be the combined effect or the algebraic sum. So, such case is not possible. So, you need a single nucleon as the target. So, an incident beam of nucleons is scattered from the target of hydrogen, because hydrogen you have only a single nucleon. So, you can have either, if this is a neutron proton scattering, or if this is a proton scattering. And incident nucleons can be scattered by individual protons. Multiple encounters are generally reduced by large spatial separations between nucleons, because our nuclear range is very small and atoms have separation of nearly more than they are in the unit of angstrom. So the separation between two hydrogen atoms is very large compared to the nuclear range. So if one nucleon is approaching the nucleon in the target, only that nucleon will be affected from the nucleon in the nucleus of the target material. There will be no effect from the neighboring atoms. So, characteristic properties of nucleon-nucleon interactions can therefore be deduced without complications. As in the case of electron scattering, the nuclear scattering problem is analogous to the diffraction problem in optics. There are three features worth mentioning. That means the first one, the incident wave is represented by a plane wave. This is the incident wave. So, we can consider it as a plane wave because the source is, suppose the source is very at a large distance, you can consider it is as a plane wave while far from the target. The scattered wave fronts are spherical. That means you just assume that a plane wave is coming and when it is hitting the target, that at a point it is diverging to, so that from the target it can move to any point or any direction after the scattering. So you can consider it as a spherical wave, and if that spherical wave you are considering at a very long distance, there also you can have the concept of plane waves, and these things are not due from your optics classes. So the total energy content of any expanding spherical wave front cannot vary. Thus, its intensity, that means per unit area, must decrease like r square. That means you know that the energy will be normally the square of the amplitude that you are normally saying. So, in that sphere, when it is expanding, actually there is no energy loss or energy gain in a scattering experiment. So, the energy must be same. And there, its radius is increasing. That means the number in unit area, you can see that the number will be changing. So, correspondingly, what we must have is the intensity must decrease as r square, that means 1 by r square, and it is r raised to minus 2. It is clear here, it is r raised to minus 2, and its amplitude must decrease like r raised to minus 1 because amplitude square you are taking. So, here you see, along the surface of any spherical scattered wavefront, the diffraction is responsible for the variation in intensity of the radiation. And this we have mentioned, the intensity is varying or the energy is varying, and that variation in intensity is due to diffraction. The intensity depends on the angular coordinates theta and phi. In spherical polar coordinates, you are familiar with the theta and phi. And a radiation detector placed at any point far from the target would record both incident and scattered waves. And here you can see that this is the incident wave. And it can go, a portion of it will be going without any scattering as unscattered wave, or that means they will go through, and a portion will be scattered. So, in this side, that means if you consider the target, and in the left side you have plane waves as the incident waves, and to the right side of this target you can see the unscattered wave as plane waves and the scattered waves as spherical waves. So, you can, using a detector, you can detect both these scattered waves and unscattered waves. And to solve the nucleon scattering problem using quantum mechanics, we assume the nuclear interaction by a square well potential as we did for the deuteron. So here also, when the nucleons are coming closer, in order to study the force between them, we must have an idea on the potential. And we are here also, you are assuming that that potential is a square well, like this. This is our square well potential. So up to a particular distance, say this R is the separation, up to capital R, it is minus V0, and after that it is 0. In fact, the only difference between this calculation and that for deuteron is that there we concerned with the free incident. Here we concerned with the free incident particles with the E greater than 0. Our particles are emitted with an energy. So in the system, the energy will be the energy or kinetic energy of the particles. And normally it will be greater than 0. And in the last case, that means in the deuteron, the energy of deuteron was its binding energy. So that is the difference. And there E you have taken as minus B. It was a negative value there. But here E is positive. And for low energy nucleon scattering, we may simplify the Schrodinger's equation by assuming L is equal to 0. That we have already done. And consider an incident nucleon striking a target nucleon just on the surface, so that impact parameter is of the order of, impact parameter you are normally writing as B. It is nearly 1 femtometer. And that impact parameter, you can visualize that impact parameter is the shortest distance between the track of the incident particle and you must have a center for your this nucleon. So it is the separation base. You can draw a line through the center of your nucleon. So it is there, and when it is coming closer, or you can track the direction of nucleon also, incident particle, incident nucleon. So it will be a straight line. Below to that, you have another line which is passing through the center of the nucleon. So this perpendicular distance is normally termed as the impact parameter, which is the term already known to you. And we are assuming that it is of the order of 1 femtometer. So that must close, we are assuming. If that means when that is close, when it is approaching, after some time, it can deviate from its path. If the incident particle has velocity v, its angular momentum relative to the target you can write as mvr. M is the mass, v is the velocity, and that r is this value. Here it is 1 femtometer. We have mvr is equal to Lh cross. Angular momentum is an integral multiple of H cross, where L is the angular momentum quantum. And if this mvr will be much less than Lh cross, when only L is equal to 0, interactions are likely to occur. This is, if this L is 0, this value is very, very small. That means this value is very small. That means this MVR must be very small. That means it is nearly very small value. Then only you can have this condition, L is equal to 0. So you can calculate the corresponding kinetic energy. This is angular momentum. Kinetic energy is half mv square. So here you can, mv is Lh cross by r. Lh cross by r, capital R is mv, or m square v square you can write as this L you are neglecting as 0. It is h square by r square. H square by r square. And also half mv square you have half here. And you are multiplying this v square r square that by h. So you have to here also you have to square as h cross square by m square. M square v square you are taking. This is just mv square. So you have to divide with the v mass. Sorry, so that is h cross square 2mr square. Now we are multiplying with the c square. H cross square c square by 2mc square r square. This quantity h cross square c square will have the dimension of this MeV into Fm. So 200 MeV femtometer square, and this mc square is the mass, which is nearly 1000 MeV. You can consider the proton mass, and this distance we have taken as 1 femtometer. So 2 is here, and on simplifying this, you will be getting it as 20 MeV. So if this energy, that means you are not considering that value L, it will be nearly 20 MeV. So if the incident energy is far below 20 MeV, the L is equal to 0 assumption is justified. So if you are using incident particles of the order of energy, which is that means of the order of say 1 MeV or 5 MeV, that is much less than 20 MeV, our assumptions are correct. So we have introduced this to show that our energy, if our energy is very small, we can have the L is equal to 0 assumption possible. That's all. So we just start with the condition that our L is equal to 0 is possible when energy is small. And this is our equation. We have already derived this in, or we have already, already know the Schrodinger equation. Del square psi plus 2m by h cross square e minus v in psi is equal to 0. And now we can write this psi as radial part and azimuthal part, and only nuclear potential, it is only depending on r. You are writing it as the product of radial part and azimuthal part, and you are removing the azimuthal part, etc. That already we have done in our neutron discussion. So after that, we will be replacing the psi with ur by r, and you can have the Schrodinger equation as d square u by dr square plus 2m by h cross square e minus v of r is equal to 0. And this v of r for this square well potential, this value of Vr is minus V0 when small r less than capital R, and when the small r is greater than capital R, Vo equal to 0. And here you are showing the energy. And in last case, here we have drawn energy here, where E was negative. So after this, we can compare the results of neutron and this scattering. So here, energy is always same. That means energy is conserved. So before scattering and after scattering, energy you can consider as the same quantity. So d square u by dr square plus 2m by h cross square E plus V0 minus Vr as minus V0. So it is plus V0 of u equal to 0 for r less than capital R, and for r greater than capital R, this V0 is not there. So it is d square u by dr square 2mv by h cross square u equal to 0. In last case, in place of this E, we have used minus B. And now what will be the solution? The acceptable solution for the region r less than capital R is, actually it is u of r is a sin k1r plus b cos k1r, that is known to us, and you are neglecting that cos term. So this is the answer. U of r is a sin k1r with the k1, it is given by root of 2m E plus V0 by h cross square. Here we are taking that value here. And last case for proton, so for neutron, this was minus B. And for r greater than capital R, the wave function is, here you have the difference, because In deuteron, here it was with the minus sign. And when you have equation like d square u by dr square minus term into u, you will be the exponential solution. And when it is plus, it must be either sine or cos. So that is why for r greater than capital R, the wave function is c prime sin k to r plus d prime cos k to r, with the k2 is equal to root of 2 mv by h cross square. So we have introduced two constants. For our sake, we are taking it as c prime and d prime. And it is convenient to write now this c prime as c cos delta and d prime as d sin delta. So you are for this equation number 4 is now c cos delta sin k to r plus d sin delta cos k to r. This is of the form. Sorry, this is also with the c sin delta. This is c sin delta, and this is also sin delta. So it will be, it is not d, I'm sorry, here it is not d, it is c, and this d prime as c sin delta. So c is common, and it is of the form sin a plus b. Sin of a plus b is sin a cos b plus cos a sin b. So that is u of r is equal to c into sin k2r plus delta. And you can make our equation number 5. So just note this. Here in place of this d, we have c. This is c and this is also c. So the boundary conditions on u and du by dr at r is equal to r. We have shown that it must be continuous. The wave function should be continuous, and when wave function is continuous, that u and its first derivative must be continuous along the boundary. That means on both sides of the boundary it is valid, and at the boundary these two values on the two regions, if you are taking it as first region and second region, at the boundary value of u at the first region is equal to value of u at the second region, and similarly the first derivative in first region must be equal to the first derivative in the second region, and this is applicable at the boundary. So we have this equation sin k1r and this one. So at boundary, c sin k2r plus delta is equal to a sin k1r, and their derivative, it is k2 c cos k2r plus delta equal to k1 a cos k1r. Suppose you divide this 7 by 6, you can get the result as k2 cot k2r plus delta equal to k1 cot k1r. And this is also a transcendental equation. And this can be solved if you know E, V0 and R. That means you have to know this k1 and k2. Suppose you know E, V0 and R. This R. You can, suppose you know E and V0. You can have k1 and k2, and also by knowing the value of r, you can solve this equation. And this term delta is called the phase shift. And what is the need for, or why it is known as phase shift, or what is the interpretation of that phase shift that we can do? So first, before that, we can make a comparison, and this was our deuteron. Minus V0 up to R is equal to R, and this you have considered as the binding energy of deuteron. Your energy was minus B, and here energy is positive and other things remain same. So for R less than capital R, the same solutions were similar. A sin k1r, and here also it is A sin k1r, and here k1 was 2m by h cross square minus b plus v0, and here we have just put it as e, and that e is a positive value. And for r greater than r, there the equation was c e raised to minus k2r plus d e raised to k2r, with the k2 is equal to root of 2mp by h cross square, and also you have a minus term there for, and here ur is equal to c prime sin k2r plus d prime cos k2r, with the k2 is equal to 2m in place of this b, we have e by h cross square. So here e is positive. That is why for r greater than r also we have a solution based on sine and cos. So this is the case. Now this is the nuclear wave function, and inside r is equal to small r is equal to capital R, we have seen that it is a sine wave. And for neutron, at this boundary or after this boundary, it is changing to an exponential form, and it is exponentially decaying. But here, inside and outside the potential well, it is the wave function is a sine function, or it is a sine or cosine, whatever may be. It is a sinusoidally varying function. So we have shown that both are sine functions. Sine, this was our equation. A sin k1r, this is the value when small r less than capital R, and c sin k2r plus delta when this is greater than, small r greater than capital. The effect of scattering potential is to shift the phase of the scattered wave at points beyond the scattering regions, where the wave function is that of a free particle. A free particle means there is no binding energy, or there is no force acting on the particles. So if that particle is freely moving, and this is the case of a free particle. That free particle means, suppose for a free particle your V0 is equal to 0. If it is a free particle, what will be the condition? For a free particle, you can see that actually this is the wave, it is going like this, there is no change. So this is the point you are getting. And you can see that when V0 is equal to 0, what is the case? You may see these two values. If V0 is equal to 0, that means this will be 2me by h cross square. K2 will be also 2me by h cross square. That means K1 is equal to K2. And when K1 is equal to K2, this is sine K1r plus delta equal to A sine K1r. And this will be valid only if this delta is equal to 0. Then only this K1r plus delta will be equal to K1r. Okay. So that is, this K1 and K2 will be same. And for attractive potential, that means when potential is attractive, you can see that this sine wave, the sine function is becoming 0 here. That means at a value before this one. And this distance you are considering as, or this value you are considering as the phase shift. So this difference, that means this minus this, that you can, it will be, that means the actual value and now the new value. So that distance will be, or that value will be greater than 0. This will be the case for attractive potential. And for repulsive potential, you can see that this sine function is just changing here. and it is meeting here. So this minus this will be a negative value. So phase shift is, for repulsive potential, phase shift is negative, and for attractive potential, phase shift is positive. How can you just consider or just explain this attractive potential and repulsive potential based on this delta? That also we can do. You can see again this equation, our quote equation. Actually, we have, for a zero potential, we have used this equation. So it is better to use this equation. If K1 is equal to K2, you can see that K1 quote, I am taking it as both K1 and K2 as K. Then K quote Kr plus delta is equal to K quote Kr. So that equation is valid only when this delta is equal to 0. So that is the case of free particle. And when it is attractive means this V0 is negative. And V0 negative, this is the equation. K1, our equation is, this is already we have done with the VR as minus V0. So you can see that this V0, this is E plus V0 and this is only E. So this K1 will be naturally, or K1 will be greater than K2. K1 will be greater than K2. K1 greater than K2. So in this equation, K1 is greater than K2. So if you want to match this quote of K2R plus delta and quote K1R, what is the condition? We can see that this K2 is less than K1. That must be remembered. For quote, you can see that when angle or K2R or K1R, whatever may be, it is increasing. The value is decreasing. The value is decreasing. At 0, cos 0 by sin 0, it is 1 by 0, that is infinity. And at a 90, that we have already done in our Deuteron also, at 90, it is 0. So here you can see that this K2 is less than K1. This value K1R will be actually greater than K2R. And when it is increasing, it is increasing, that means this value increasing, the value we are decreasing. So when this K2R is decreasing, so in order to make it, that is K2R is less than K1R, in order to make that value equal, you have to add a term with the K2R. Then only that K2R will be equal to K1R. Normally you can see that K2R will be less than K1R. And when quote of these two functions should be same only when this K2R is becoming equal to K1R. And for that, you have to add a term with this K2R to get these two values equal. That is why you can say that this delta is a positive value. Delta is positive or phase shift is positive. By adding that value, you can get these two matched so that is a condition. That is why you are saying that the delta is positive. And when in a repulsive potential means your force is negative. Force is repulsive means your potential is positive. Always for attractive forces, our potential is negative, and for repulsive forces, potential is positive. So if this V0 actual value of V0 is plus V0, this equation becomes E minus V0. So when it is E minus V0, this K1 will be less than K2. K1 less than K2. So K1 less than K2. You can see here this K1R is less than K2R. So value of K1, this value will be greater than this value. This side, K1R will be greater than K2R. So K2R is greater than K1R. So you have to decrease that K2R. Then only the value of your K2R will be equal to that of K1R and you can get equal values. That is why this delta should be negative. And this is some basic concept. And you can, from the figure also, you can directly say that the phase shift is positive or negative. But this is another way of explanation. So, and this is, so from here also you can have an idea. But a more detailed explanation can be given if you have the partial wave analysis. And that we can do in the next class. And thank you.